Welcome to another podcast. This episode we're going to be taking a look at what is called the characteristic coordinate method. This is sort of a direct follow-up to the previous video where we looked at characteristic curves, or the method of characteristic curves. And I want to take a look at an example that uses that idea, but in kind of a roundabout way. So let's take a look at the following partial differential equations. We're going to stick with the first order PDE. And I'm going to kind of wreck our day a little bit by throwing in this u. And I'm actually going to make it inhomogeneous by throwing in the variable t over here. So this is a PDE which we don't really know at this point how to handle. Because up till now all we've been able to do are things that look like this by using the characteristic curves. In other words, the fact that if you look at dx dt equals, let's say in this case it's b over a, that the characteristic curve here has the property that it's x equals b over at, that's constant. So if I multiply through by an a, I get ax minus bt equals c. So my characteristic curve, phi of xt, is ax minus bt. So everywhere the PDE is constant along the line ax minus bt. Well, I can sort of use that here by forgetting that I've got the negative u and the t in the problem. And if I just focused on u of t plus 2u of x, then b obviously is playing the role of 2 and a is playing the role of 1. That would seem to suggest that x minus 2t might be a characteristic coordinate for this. That's constant. And so if you recall from class, we looked at characteristic coordinates, and it seems to me like the approach here is to define my characteristic coordinates as x minus 2t for the position variable, and then let time just basically stay the same as it is. This says that we're orienting the axis basically so that the position axis follows the characteristic line. Meaning that hopefully when we make this change of coordinates, we won't have two different things varying. We won't have both position and time varying. We'll just have time varying because of the coordinate change that we're making. And so in order to make this change of variables, I've got to do a little bit of chain rule here. So I need to change u of xt over to u of xc tau. I'm going to start with u of t. So u of t in terms of the variables xc and tau is u of xc times xc t plus u of tau times tau with respect to t. And so you can look, u of xc is the unknown partial. xc with respect to t is negative 2 plus u of tau is an unknown partial. Tau with respect to t is 1. U of, in this case, x, we get u of xc times xc with respect to x plus u of tau times tau with respect to x. So u of xc, once again, is the unknown partial. Xc with respect to x is 1. And u of tau times tau with respect to x is 0. So finally, if I look at putting the differential equation back together, my equation was u of t plus 2ux minus u equals t. So making the change over to the variables xc and tau, we have u of t is negative 2u of xc plus u of tau, plus 2 times u of x would be 2u of xc, minus u equals t changes over to tau. So if things worked correctly, we should get the position variable to cancel out, and it does, leaving us with u of tau minus u equals tau as our new PDE. But it's not really a PDE because only one variable is changing, so I can think of this as if it were the ODE u prime minus u equal tau. And so this is a first order linear ODE, which means we use something called the integrating factor method on it. So the integrating factor here is mu was one of the things that we used for it. It's e to the negative integral of whatever is the coefficient of this term, which is -1. So that's negative 1d tau, which is e to the tau. So that is our integrating factor. Sorry, it's e to the, I don't need two negatives, just one. So it's e to the negative tau, excuse me. So remember, it's if you have u prime plus p of t u equals, it doesn't matter what's on that side, then the integrating factor is e to the integral of p of t dt. And so that's all I'm applying here for my integrating factor. So my integrating factor is e to the negative tau, so I'm going to multiply this equation through by that integrating factor. And when I do that, the left-hand side should collapse into this product, which it does. And then the right-hand side is as is. If I integrate both sides, then that gives me e to the negative tau u equals the integral of tau e to the negative tau d tau plus an arbitrary constant of integration. Now, here's where you have to remember that this is still a p to e, so there is a second independent variable. So constant with respect to tau means any arbitrary function of the other variable, which in this case is xc. So if I multiply through by e to the tau, I get this. And so I have an expression here for u in terms of tau and xc that I need to now turn back into my answer for x and t. So let me create a little bit of space here. And so if I do the integration, then this is e to the tau times this integral here, t e to the negative tau. If I do that integration, then what I'll end up with is, well, if I do the entire integration, what I end up with is negative 1 plus tau. So if I include the e to the tau, basically I end up with negative 1 plus tau times e to the negative tau and then multiplied by e to the tau. So the e to the negative tau's cancel out. Plus g of xc e to the tau. And now if I transform back into my x and t variables, this u, which is a function of t and xc, or tau and xc, becomes a function, once again, of u of x and t. And this becomes negative 1 plus t plus g was x minus 2t for the xc variables. This is x minus 2t. E to the tau gets replaced with t. And so this turns out to be our general solution for this particular problem. Now, it's sort of a long road here, but really there's not much difficult going on. All you're doing is changing over the variables to end up with a new equation. So if you kind of think about the steps that are involved, I kind of bracket everything as we go along here. The steps that are involved basically is just 3 steps. The first step is come up with your change of coordinates based off of this idea that we talked about here with characteristic coordinates. Then the second step is use those characteristic coordinates to turn the PDE involving two things that are changing into a PDE involving only one variable that's changing, which basically means it's an ODE. And then solve the ODE. That's where it'll be different on each problem. Here we had to use integrating factor method. We might have to use separation of variables or any of the other methods we learned in ODE. But you solve the ODE, and then once you have the ODE solved, you basically back substitute or you replace all the taus and xc's with x's and t's for your final answer. And so that is basically the idea behind using characteristic coordinates or making a change of coordinates to simplify a problem that was a PDE into a problem that's essentially an ODE. We're going to see more of this in the coming lectures, and so I wanted to take the opportunity to work a couple of problems in a little bit more depth because the book doesn't have a lot of practice on this particular topic. All right, thank you for watching.